Welcome. You're all welcome to FANOG Research Group monthly meeting. Usually we have a meeting every month, and we invite accomplished scholars all over the globe to give us talk, and that will help to build, especially the young researchers. It's a form of mentorship. And usually, like we said, we invite well-known and accomplished scholars to give us some talk based on their areas of research. And this month of, please kindly mute yourself so that Mohammed, please mute yourself so that only the speaker can talk. Okay. So I'm trying to mute people. Please try to mute when you join. Many people are still joining, so we are admitting them. So, like we said, this month of October, we are glad to have Dr. Sulyman Olakunle Salawu of the Department of Mathematics, Bowen University. Dr. Salawu is not just he's not a mean person in research. He's well known.
I'm assuming it now.
And he has actually published so many work. In fact, about 150 of his papers are in Scopus. And the recently released top 2% researchers in the world. He was listed among those top 2% in the world by the ranking of Stanford University in the US. So he's a well-known author, and his paper, as I said, he has about 150 papers in Scopus and over 1,900 citations. So that's to tell you the kind of scholar we have here today. So it's a privilege to have Dr. Salawu present to us this month. The title of his presentation is titled Thermal Stability of Magneto-Hybridized Silicon and Aluminium Oxide Nanoparticles in C3H8O2 Williamson Exothermic Reactive Fluid with thin radiation for Perovskite solar power. It's a long title, and I'm sure Dr. Salawu will do justice to the topic. So we are glad to have Dr. Salawu, an accomplished scholar, present to us part of his research in this October 2024 series of FANOG meeting. So Dr. Salawu, we thank you for accepting our invitation to present to us your work. So we now yield the floor to Dr. Salawu to make his presentation. You're welcome, Dr. Salawu.
Okay. Thank you, Dr. Okeke. I'm so grateful for the privilege to be speaking to scholars around. I've seen a partner who is also, that is Tijani Yusuf. Okay. I recognize you. And so I will be speaking on the topic that is presented, that is showing on the screen. That is thermal stability of magneto-hybridized silicon and aluminum oxide nanoparticle in propane glycol Williamson exothermic reactive fluid with thin radiation for perovskite solar power. We actually choose today, or I choose this topic because of the new evolving of perovskite solar power, apart from the usual solar system we use, the usual photovoltaic system we use. So in this, the interest is just to increase the thermal stability and energy conservation. So all over the world now, the interest has been to improve the power generation, which is of eco-friendly. And with this, several researches has been done on this, especially on solar energy, renewable energy, and the likes. So I have now come up with this particular idea, and different fabrications have been done just to improve the technology of renewable energy. So, but perovskite solar power technology is the next emerging generation of photovoltaic thermal power system for an enhanced and stable power supply. So we consider this as because of it's a new trend. It's just coming up, just evolving, and people have not been. So though there are several works on it, most of them are position paper, but we just try to come up with this from the perspective of fluid mechanics and see if we combine two or more, or one or two or more nanoparticle. We just want to see the effect of nanoparticle, because nanoparticle is one of the research is one of the current technology in fact, there is no area of life or aspect of engineering now, science, you see them talking about nanotechnology, nanomaterial, nano this and nano that. So we consider a nanomaterial. So we are looking at silicon because we choose silicon because of the properties of the silicons, and we choose aluminum oxide because of its properties. So, well, most of the photovoltaic thermal system, the solar power, they have been using silicon. Most of the ones we see around us are silicon-based solar cell or solar power. So, and we also consider Williamson field, which happen to be a non-Newtonian field, energy. It has to do with sun radiation and things like that. So we consider a special radiation, which is called optical thin radiation. Most of the common radiation that has been used in papers in research has been thick radiation. So we consider this thin radiation, which is what a condition in radiative transfer, where a medium does not absorb or scatter a significant amount of the radiation passing through it. So we are looking at a case where the radiation that is being absorbed will be concentrated into a particular direction, and it will not be scattered as we normally observe in the thick radiation. And also, this project examines the thin radiation thermal stability of combined magneto-hybridized silicon oxide and aluminum Perovskite thermal cell improvement. So in the area of Perovskite have become a significant for energy feed because they offer several advantages over the traditional silicon-based solar cell. So just as I said, most of the solar power cells that we see around are made from silicon. So we also consider silicon as part of the material here, as part of the nanomaterial. Then silicon and aluminum are being hybridized in order to improve the solar cell of the photovoltaic cell of perovskite solar system. So one of the advantages of this perovskite solar system is high efficiency. The cell have impressive power conservation efficiency in a relatively short development period, surprising 25% compared to the silicon solar cell. So, and also one of the advantages is lower manufacturing cost. The fabrication process for perovskite cell can be simpler and less energy intensive than that of a silicon cell. Then one of the advantage of the perovskite solar power is that the material can be fabricated in such a way that it can be flexible. That is, you can bend it. You can bend it to any direction, unlike the normal silicon-based solar cell, that it has to be flat and it cannot be bent, cannot be just have to put it on a flat surface. Otherwise, you will not get the best of it. But for perovskite solar cell, so the material can be made flexible so that for enhanced performance. So these are some of the future challenges as recorded by several researchers that have talked about or looked into perovskite solar system. Despite the advantage, there are challenges to be addressed. One of it is the stability. And that's why this particular study, we are looking at the thermal stability of the perovskite material. So perovskite material can degrade when exposed to moisture, oxygen, or light, impacting the long-term stability of the solar cell. Also, some of the components in the building or development of the perovskite solar cell is the lead content. As we all know, many lead has adverse effect, especially when it is contaminated with the environment, and it can lead to health challenges and the likes. So researchers are exploring lead-free alternative, but they tend to have lower efficiency. So several researchers, because of the effect of lead in perovskite cell, so many researchers have looked at different materials in order to eliminate lead, so that we have to bring in silicons and mineral oxide, so that we look at the possibility of improving the performance of this solar system. So these are the field objectives of the study. One of them is to enhance the thermal behavior of the material, of the hybridized material, for enhanced solar energy. Then we also we look at the interaction of the nanoparticle, because we all know that nanoparticle has a better thermal conductivity than traditional liquid or solvents that we use. So we study the thermal properties and the effects in enhancing the thermal stability and enhance the thermal properties of the silicon and aluminum oxide. So the synergy between the two of them in enhancing the performance. So we also consider thin radiation, just as I said. So to examine how thin radiation heat transfer influence the performance and thermal dissipation characteristics of the nanofluid, especially under conditions similar to concentrated solar power. So all the interest is just to look at the efficiency of perovskite solar cell. So to analyze the potential of magneto-hybridized fluid as an advanced thermal management medium, reducing overheating and enhance the efficiency and lifespan of perovskite solar system. So these are some of the application of perovskite solar system. So enhanced thermal management in perovskite solar cell, efficient energy harvesting in concentrated solar power system, nanotechnology, enhanced heat transfer fluid, improved stability for thin film solar panel, advanced cooling system for renewable energy device, then scalable solution for solar power storage. So these are some of the advantage of this perovskite solar cell compared to other things, and the advantage of the material that is being considered for this particular study. So that takes us to the basic model. The basic model for most of the fluid model has always been built around Navier-Stokes equation. So we have in this particular study, we are actually focusing on two equations apart from the boundary condition. So we consider the momentum equation. This momentum equation is built around the Navier-Stokes. So this is the basic Navier-Stokes equation. And we have this, the mu here is the viscosity. So the viscosity sometimes can be taken to be constant and can be taken to be variable. It all depends on the interest and the focus of the research. So then there's a gravity here. So if in a case we are considering a system that is being influenced or gravity driven, so this gives the basic Navier-Stokes equation, and we have the temperature here. So, and that is that for, so said the momentum equation describes the motion of a fluid particles due to forces acting on it, such as pressure, stresses, and external forces like the feed. So this is the basic. Also, because of that is based on the first week. So here give the basic energy equation. We have the specific heat capacity, the specific heat at constant pressure. We have the thermal conductivity K. Yeah, this defines the thermal conductivity, and this phi here talks about the physical dissipation, that is representing the conservation of kinetic energy into conversion of kinetic energy into heat energy due to viscosity. So that's what this term here stands for. Is F to convert the kinetic energy to heat energy due to viscosity. Then the Q here talks about the heat generation. So we talk about the heat generation. So here is the first law of thermodynamic energy equation. The equation describes how the internal energy of a fluid changes due to heat transfer, work done by forces, and heat generation. So that is the base. So for this particular, for our own interest model, so this gives the descriptions of the model and the assumptions of our own model. So what we give earlier, I mean, those two models that was given earlier are the basic equation for the energy and the momentum equation, which are based on the first law of thermodynamics and the Navier-Stokes equation. So for this particular study, these are the fuel absorption that is being considered for this particular study. So we consider an isotopic silicon oxide and aluminum oxide hybridized nanoparticle propagated in an exothermic reactive propane-glycol-Williamson working fluid. So propane-glycol in this Williamson fluid are considered to be the base fluid. And the base fluid, the propane-glycol is an alcohol-based fluid. And the Williamson is a non-neutronial fluid. So this is being considered for solar power improvement and stability. The working base solvent and nanoparticle are influenced by thin radiation, Lorentz force, physical heating, and bimolecular reaction kinetic. And the fluid temperature is taken to be at 10 degrees centigrade. So that's the nanoparticles, silicon oxide and the aluminum oxide with the respective volume fraction. So these are taken to be the volume fraction. And it's assumed for different heat conductivity, thermal capacity, electric conductivity, density, viscosity, and Williamson and viscosity. So a Williamson-Cauchy model is employed for the viscoelastic induction at time t greater than 0 for a stable and continuous solar generation in a fixed flat channel. So, and we have this in a fixed flat with B as presented in schematically in figure 1 and 2. So without the formation of the polyeder nanoparticle material, so we assume that there is no deformation in the material and there is no agglomeration, that is, there is no clustering of the particle. So, and to avoid clustering of the particle is an agent can be added, which we refer to as a surfactant agent. So this is the typical model for this study. So the first figure here actually describes the configuration for perovskite solar. Then here is the flow dimension of what we considered here. This gives the main governing equation. The first equation here, sorry, no, there's some equation before now, but because I thought I would be able to run a beamer for this presentation, but the beamer failed to work on my system, so that's why this thing started from. I have to screenshot to build the slide. So that's that. So the model governing equation. So we have the first equation that talks about the continuity equation for a flow. There must be a continuity equation. Then the second equation, which signifies equation 5, is the momentum equation, a modified momentum equation, still satisfying the Navier-Stokes. So, but we, in this particular one, we consider a Williamson. Instead of the Navier-Stokes, just consider a normal Newtonian fluid. So here we have to consider a non-Newtonian fluid, which is Williamson. The essence of non-Newtonian fluid is just to enhance the viscosity of the system. So that's why we consider this. So there are several non-Newtonians, but we only pick interest in this because of its special properties. Because at low and high temperature, it behaves as a Newtonian fluid. So that's why we just want to look at this. So other researchers can also pick the same work and look at other nanomaterial and look at what's the behavior and the strength of that material. So also, the equation 6 here give the energy equation, the modified energy equation from the first law of thermodynamics. So the equation here actually define the exothermic reaction. Then this gives the radiation. Then if a Joule heating is being considered, so that's why we have the radiation, the magnetic tank coming into the equation. And the last time here actually defined the viscosity. The heat dissipation, the physical heat dissipation. And here we have the figure 7 here that is stand for the boundary condition that's been considered for this particular problems. So when it comes to fluid model and fluid problems, it all depends on interest. There are several parameters that one can consider. They can also look at other cases of parameter when it comes to fluid model. And the boundary conditions all depends on the interest too, on the architecture of your geometry. The configuration of the geometry has to do with the boundary condition, and the geometry must definitely satisfy. Otherwise, the whole thing would be opposite each other. So the boundary conditions and the geometry being considered have been taken. So we consider, we are from the boundary, from the channel, from this geometry, we assume that the upper surface is being exposed, there is a convective cooling on the upper one, while the lower one has no convective cooling. So that's what you see here. So, no, sorry, it's not a convective cooling, sorry. An asymmetric heating, I want to say, sorry. So there is a differential time. Okay, this is not asymmetric, sorry, it's not asymmetric. I'm taking it for another thing. So that is what we considered here. And this is the boundary condition, but it actually satisfied the geometry that was given up there. So the model equation still continue. And here we assume a thin radiation, which is the Q dy minus the Q dy that is here. So the thin radiation is assumed, and that can be redefined to be this. So where C is taken to be very less than 1, and is assumed, and the approximate equation for the radiation flux is given as this. So the radiation flux for optical thin radiation is being considered, and that is what is given as equation 9. So because we consider a nanomaterial, so for nanomaterial, these are the model for nanomaterial. We have this one that talks about the density for nanofluid. Sorry, that talks about the density for the nanofluid. Then this is the viscosity for the nanofluid. And then this one defines the thermal conductivity of the nanofluid. And here talks about the electric conductivity of the nanofluid. And here also, so almost like the first one, this actually defines the nanofluid, and this defines the hybrid nanofluid. So we have the hybrid, that's why you see subscript of HF. This is hybrid nanofluid. The density, the viscosity, thermal conductivity, and the electric conductivity are all given as this. So, and these are the properties, I think the properties of the material being considered. We consider the silicon oxide, aluminum oxide, and propane glycol. So these are the density of each of these material. Then this gives the thermal conductivity of the material, and here also consider the electric conductivity of the material, and this gives the heat capacity at constant pressure for the material being considered. So these are experimental value. It's not just a value that was picked, but the experimental value that satisfy the properties of some of this material being considered as for the nano. So the model transformation, and to demonstrate the applicability of the model, a transformation of the mathematical model along with the initial and boundary condition is carried out using the quantities below. So these quantities have been used to transform the boundary, the main governing equation. The transformation is very necessary because we have to non-dimensionalize so that we can have a realistic model. The realistic model, then we'll be able to get some of the basic thermodynamic fluid properties, where we talk about the viscosity, dissipation, magnetic, and Plan2, like that. So it is necessary to non-dimensionalize so that we can easily have some of the thermodynamic terms coming up in the model. So on transforming so we use all this on the given model along with the hybrid, the nanomaterial, the nanofluid definitions, and the hybrid nanofluid equation that was given earlier. That is, I'm referring to this and this. So this equation 10 and that of 11. Then so what I did okay, let me just explain here because so that we not miss it up. I have to use all these values. All these values, I have to use them on this equation 9 and 10. On this equation 10 and 11, so say. I have to use it on the equation 9 because these are values that must go into this. So I wrote a code. From the code will take the value and give me the real value for the density of the material being considered. So that, because I have to be more we have to use experimental value so that, because these are material that has specific properties. So we choose to use the experimental value and their main properties, their main thermal properties to compute this study. So those values are being used on this and on this. So we could generate a single value for the density, for viscosity, and the likes. So with the help of this value given in the table, and the non-dimensionalization was done. So when the non-dimensionalization was done, we have this. We are Q1, Q2, Q3, 4, 5 at the nano quantities. At the nano quantities. So then we have here talks about the velocity, the velocity with respect to time. Then this define the viscosity. Then here give the magnetic Hartmann number, that is the magnetic term. Then we have the Plan2, we have the thermal conductivity here, and also here give the physical dissipation, that is the Brickman. So because we are considering an exothermic reaction, so that's why we term this to be Brickman, because some of the terms that came up when we non-dimensionalize. So this actually stands for Brickman, unlike the normal way we have it in normal fluid material. So because of the exothermic term, we have to bring in a new quantities or a different quantity to non-dimensionalize the problem. So we have this, and this is the exothermic reaction. The beta here is talking about is the activation energy, and here is also the pigma, because this has to do with the Joe eating. This has to do with Joe eating, and this has to do with viscous dissipation. Then the transformation of the boundary condition also give this. So the quantities or the variables that you use for transformation all depends on the problems. It all depends on the model, because the model I gave here, the transformation that has been used here, these quantities that is being used for the transformation may not be applicable for some problems. But for this particular one, this is what was used and it was actually applicable. But in a case where we cannot find a suitable one, we can always use a localized transformation. We can use a localized quantity to transform the model, which we normally refer to local similarity. In case we cannot find a good quantity to transform the model, so local similarity can always be appropriate, because that will be for specific model. So, and it can undo the problems being considered. And so, but for this particular model, these are the transformation is obtained as so the quantity. So because the model is an unsteady state problem and it's in form of PD, it's a PD problem. That's why you see that it's a partial differential model. And for us to solve this, and it's still unsteady, for us to solve this, we have to use to solve the problems, because the model has a closed form solution. So we have to use a finite difference method, a semi-crystallized finite difference approach, which is referred to as line method, is being employed to solve the problem. So here give the decrystallization of the momentum equation, and this gives the decrystallization of the energy equations and the boundary condition respectively. So for us to, because this is at this stage, every mathematicians, especially people in applied mathematics, must know how to use one or two software to solve their problems, because some of these problems are not problems that you can say you want to use your paper and pen to solve. And that way you will spend longer time on it, and okay. Sorry, my system was muted mistakenly by the host. So, for anyone that is in applied mathematics must.
Sorry, Dr. Salawu. Thank you. I want to